right, so we are going to be taking a look at tangential and normal components of acceleration here. And since this is a math class and not a physics class, we're not going to dive too deep into the meaning behind all of these things. This kind of falls into the category of if you can memorize some formulas and take some basic derivatives, you can get these questions correct. But essentially, breaking acceleration up into its tangential and normal components gives you a little bit more insight on how your velocity is changing, not just in magnitude, but also in direction. So essentially, the tangential component of acceleration tells you how much your speed is changing, and the normal component of acceleration tells you how much the direction is changing. So if you imagine you're traveling in a car going 50 miles an hour, so you're going a constant speed of 50 miles an hour, if you make a left-hand turn, your overall tangential acceleration is still going to be 0 because you're still going 60 miles an hour. Nothing is slowing down or speeding up. So your tangential acceleration would be 0, but you've all experienced this before where you're traveling in a car and you turn to the left and all of a sudden you feel your body kind of push over towards the right. That's due to the normal component of acceleration because that's telling us how the direction in which you're headed, so the direction of velocity, how that is changing. Okay, so that's the idea behind tangential and normal components. It kind of gives you a little bit more insight into how your speed is changing or how the direction of velocity is changing. So basically, any acceleration vector can be broken up into the tangential component and the normal component. This part right here is called your tangential component of acceleration. This part right here is called your normal component of acceleration, and we have formulas for each of those things. The tangential component of acceleration, yes, there's a whole bunch of formulas you can use. I prefer this formula right here. That's the one that I'm going to use, but it's the same thing as this formula right here, which is the same thing as this formula right here. Just 3 different ways to write the same thing. And similarly, your normal component of acceleration has a whole bunch of different formulas. I tend to like using this one, but again, you can use any of them. And then here's formulas for your t of t, your unit tangent vector, and your unit normal vector as well. All right, so let's do an example, make sense out of all this stuff. I'll kind of show you the 2 common ways that I've seen this asked before. So this says let r of t equals this vector right here. Part A says find the tangential and normal components. So when they're talking about a tangential component, they're just talking about that a sub t. And when they're talking about a normal component, they're just talking about that a sub n. Okay, so that would be this part here and this part here, not this part or this part. So I'm going to go ahead and write down that formula for a sub t. The one that I'm going to use anyway. So a sub t is going to be equal to r prime of t dotted with r double prime of t over the magnitude of r prime of t squared. So we've got a whole bunch of things that we need to find. First of all, we know that our r of t is this right here, so let's go ahead and start taking some derivatives. That means our r prime of t is going to be 2t, 2, and 1 over t. And it means that our second derivative is going to be 2, 0, negative 1 over t squared. Now, the other thing I'm going to do while I'm here just kind of doing some computations is I'm going to plug in my t value into each of these. So r prime of 1/2 is going to be 2 times 1/2, which is 1, 2, and 1 divided by 1/2, which would be 2. I'm actually going to go ahead and find the magnitude of that as well, just so I have everything I need right here. So the magnitude of r prime of 1/2 is going to be the square root of 1 squared plus 2 squared plus 2 squared. So that's going to give us root 9, or 3 overall. And then I'll also plug in my 1/2 into our second derivative, which would give us 2, 0, and negative 1 divided by 1/2 squared would be negative 1 divided by 1/4, which would be negative 4. Also worth noting, this is also known as our v, not v prime, just v, because derivative of position is velocity. So you can't see that. That's also known as our v, and then this one over here is also known as our a, acceleration. So it looks like we have all the pieces we need to find our a of t, so let's go ahead and do that. This will give us overall that a of t is equal to the dot product of r prime of t, so 1, 2, 2, dotted with 2, 0, negative 4. I just realized I put a squared here by accident. There should not be a squared there. My apologies on that. Divided by the magnitude of r prime of t, and the magnitude of r prime of t is 3. So when we compute that, if we compute the dot product, 1 times 2 is 2, 2 times 0 is 0, 2 times negative 4 would be negative 8. So overall, that's going to give us negative 6 over 3, or in other words, negative 2. All right, so that's our a of t, and now let's compute our an, our normal component of acceleration. So again, there's a couple different formulas that you can use here. I'm going to use the formula that an is going to be equal to the square root of the magnitude of our acceleration squared minus the absolute value of our tangential component of acceleration squared. So acceleration itself is a vector, but a sub t is a scalar. So that's why this is magnitude. We have the double bars here, and this is absolute value, single bars, because it's a scalar and not a vector. So overall, we already know the acceleration vector, that r double prime. We never computed its magnitude though, so let's go ahead and do that. So the magnitude of r double prime is going to be square root of 2 squared plus 0 squared plus negative 4 squared. So that would be root 20. So if we're plugging into that, that would be root 20 squared minus our at, which is negative 2 squared. So that's going to give us root 20 minus 4, root 16, which would be 4. So overall, our tangential component is negative 2, and our normal component is 4. And a lot of times, this is where they will tell you to stop it. A question, because honestly, if you can get to this point here, then just decomposing the entire acceleration vector like we're going to do in part B, there's really nothing more to it. It's just a lot of arithmetic at this point, but we're going to go ahead and do it anyway. So part B says now to decompose your acceleration vector into tangential and normal components. So if they want us to decompose it, they want us to write it as our tangential component times our tangent vector plus our normal component times our normal vector. Okay. And we already know a lot of these things. So remember, we already know that our acceleration vector at this point in time is 2, 0, negative 4. We know that our tangential component or coefficient here is going to be negative 2. We know that our normal component is going to be 4. Okay, so that would be, we have this, we have this, we have this. We just need to solve for this one and this one. So our formula for our tangent vector, our t of t, if we look back on that previous page, our t of t is equal to v of t over its magnitude, or in other words, we can say v of t over its magnitude, which is really the same thing as saying r prime of t over its magnitude. And we have both of those things already at 1/2. So that's going to be our r prime of 1/2 was 1, 2, 2. And its magnitude was 3. So overall, our t is going to be 1/3, 2/3, 2/3. So that gives us this component here. And now that we have everything except that normal vector, we can solve for the normal vector by just plugging into this equation here. So we know that our a is 2, 0, -4. Our a sub t is -2. Our tangent vector, t of t, we just computed to be 1/3, 2/3, 2/3. And then it's going to be plus our normal component, which is 4, times our normal vector that we're solving for. So all we need is just a little bit of arithmetic here. This gives us 2, 0, -4 equals -2/3, -4/3, -4/3 plus 4n. So if we wanted to solve for n, we would say that n equals 2, 0, -4 minus this guy, so minus -2/3, -4/3, -4/3. And then that's what 4n would equal, so if we wanted to solve for n, we would divide that all by 4. All right, so let's see, if we do that, that is going to give us 2, which would be 6/3, minus a negative, so plus 2/3. Then we have 0 minus a -4/3, so that would be 0 plus 4/3. And then -4, which would be -12/3, minus a negative, so plus 4/3, all divided by 4. All right, so let's see. That's going to give us 8/3, -8/3, 8/3, 4/3, shimmy that in there, and -8/3, all divided by 4. Or, let's see, 8/3 divided by 4 would be 8/12, which would be 2/3. 4/3 divided by 4 would be 1/3, and then that would be -2/3 for our n. So if we wanted to write this as a decomposition of our acceleration vector, we would say that acceleration, again, is equal to at times t plus an times n. And now we have each of those components. Our at was -2. Our t was 1/3, 2/3, 2/3. Our an was 4, and then our n we just found to be 2/3, 1/3, -2/3. And now our acceleration vector is decomposed into its tangential and normal components.